In this video, we are going to discuss about lead compensator. So here, lead compensator is an electrical network which produces sinusoidal output having phase lead when a sinusoidal input is applied. This is the network of lead compensator. Generally, it will produce a sinusoidal output when sinusoidal input is given with a phase lead. So, whenever you give a sinusoidal signal as input, it will produce the same sinusoidal signal with lead phase or phase lead. So, here I am going to analyze this lead compensator. I am going to take the Bode plot for this. So, here I am going to consider that compensation gain. The transfer function of this lead compensator can be taken as Gc of S is equivalent to S plus Z by S plus P. This is the general transfer function of any compensator. So, in place of P, I can take Z by alpha, or alpha is equivalent to Z by P. So, you can consider alpha is equivalent to Z by P. So, in place of P, I can take Z by alpha. So, if you want to write in terms of Z, in terms of zeros, so then you can write like this: S plus Z divided by S plus Z by alpha. Whenever you are analyzing the compensators for stability, you need to consider zeros in reverse. So that means you need to consider 1 by Z when Z is there. So here I am considering like this: S plus 1 by Z divided by S plus 1 by alpha Z. Now this is equivalent to, so here we are having Z is greater than 0 and alpha is always less than 1. So Z is greater than 0 and alpha is less than 1. So now here I am cross multiplying this. How what I am going to get here is S plus 1 divided by, so S alpha into Sz plus 1. So here I will get 1 by alpha. So 1 by alpha Z, if you take in alpha Z, so this alpha will come to numerator, alpha into S plus 1 by 1 plus alpha Z S, you will get like this. So now this is general transfer function of a lead compensator. Now what I am going to do, I am going to consider j omega in place of S. Why? Because when you are going to consider Bode plot, then you need phase of the transfer function and you need magnitude of transfer function. For that, you need to consider this transfer function in j omega domain. So that means I am going to consider j omega in place of S. So Jc of j omega is equivalent to alpha into j omega plus 1 divided by, so here I am having, so j omega alpha Z plus 1. For simplification, I am neglecting this alpha. Why? Because here, as I told you, Z greater than 0 and alpha is always less than 1. So here I am considering like this: alpha is very smaller value than 1. So I can neglect this alpha. For simplicity, I am writing this as j omega plus 1 divided by j omega alpha Z plus 1. This is my general transfer function of any lead compensator. Now, if I want to consider angle of this Gc of j omega, angle of this compensator or phase of compensator, phase phi is equivalent to, how we will take phase, Gc of j omega. This is the phase of compensator. So you can see the numerator j omega plus 1 is there. So we can write like this: tan inverse, so j coefficient is omega, so another term is 1, so omega by 1, omega only, tan inverse omega. In the denominator, when you are writing denominator, put minus, so minus tan inverse, again here the multiple of j is omega alpha Z divided by, so we need to consider, so here we forgotten something to write here. Why? Because yes, when you are taking like this, you need to write Sz plus 1 by. So Sz plus 1 by alpha Sz plus 1. So here you are having another z. So here you forgotten to write another z, no problem. So when you are writing this omega z tan inverse omega alpha z divided by 1. Here you can see. So J coefficient is omega alpha z divided by, so real term is 1. So now I am explaining once again total this analysis. GC of S is equivalent to S plus Z by S plus P, where P is equivalent to Z by alpha. For analyzing compensators, I need to consider 1 by Z in place of Z. So that's why I am considering like this. So here I am cross multiplying this term, I am getting like this. After cancellation I am getting like this. As I need to consider the Bode plot, in that I need phase and magnitude of transfer function. I am converting this S domain to J omega domain. I am just putting S is equivalent to J omega. I just substituted S is equivalent to J omega in this. As alpha is very less than 1, so I am neglecting alpha for simple calculation. I am writing like this. Now I am ready with transfer function in J omega form. Now I can take phase and magnitude. So here phase phi is equivalent to GC of J omega, that is equivalent to tan inverse of numerator term. How we can write phase angle means tan inverse of, so in numerator this is in A plus JB form. Whenever A plus JB form is there, minus B by A we can write in tan inverse. So tan inverse B means J coefficient omega z divided by real term is only 1. Omega z by 1, no need to write omega z by 1. So I am writing omega z. Minus, why I am writing this minus is the remaining term in denominator. Whenever you are writing phase, when the term is in denominator, then you need to consider minus. Minus tan inverse, again J coefficient is omega alpha z divided by, so real term is 1. So no need to write that one. So we got this phase angle. So this is the phase angle tan inverse omega z minus tan inverse omega alpha z. So here I am writing tan phi value. So here if I consider tan phi, then omega z minus omega alpha z divided by 1 plus omega square z square alpha. So this is tan phi value. Why? Because both sides if you consider tan phi is equivalent to tan A minus B form will be there. Tan A minus tan B by 1 plus tan A tan B is the formula. So when you are writing tan A, tan of tan inverse omega z, so you will get omega z. When you are writing tan B, tan of tan inverse omega alpha z, 1 plus tan A tan B means omega z into omega alpha z will be there. Then you are getting tan phi is equivalent to this one. So now here maximum compensation value can be obtained at d phi by d omega at omega is equivalent to omega m is equivalent to 0. This is maximum compensation condition. So we need to substitute in this condition. Before getting into this condition, we need to know about what is omega m. Omega m is equivalent to root of omega c1 into omega c2. Whatever you consider here, these two, so this is omega 1, we need to consider omega c1 and this is omega c2. So now this is equivalent to root of 1 by z into 1 by alpha z. So this is equivalent to root of 1 by alpha z square. So you can write z root alpha. So, this is your omega m. Now, in this condition, you need to substitute this z root alpha. That means, so here this is tan phi. So, in this condition, if you substituted omega is equivalent to omega m, that means 1 by z root infinity, then how you will get, you see. So, when you are substituting omega is equivalent to omega m in this, how you are getting, you can see. So, here you are getting like this, I am just substituting omega is equivalent to omega m. So, I am making this condition, you can see. So, 1 by z root infinity, I am considering 1 by z root infinity in place of omega m. So, here I am considering this omega as omega m, that omega m value I am considering z root infinity. So, here 1 by z root infinity into z minus 1 by z root infinity into not infinity, it is alpha. So, alpha z divided by 1 plus omega square. Omega square means again we can consider 1 by z square alpha into z square alpha. Z square alpha will get cancelled, and here I am having z cancellation and z cancelled, and alpha here I am having root alpha. So, this is equivalent to I am having 1 by root alpha minus root alpha divided by, so 1 plus 1 means 2. So, this is equivalent to 1 minus alpha by 2 root alpha we are going to get. Tan phi is equivalent to 1 minus alpha by 2 root alpha. When you substituted omega is equivalent to omega m. When you substituted omega is equivalent to omega m, you are going to get tan phi is equivalent to 1 minus alpha by 2 root alpha. So, you can see. So, now what I am going to do is, so tan phi is equivalent to 1 minus alpha by 2 root alpha, I need phi. So, phi is equivalent to tan inverse 1 minus alpha by 2 root alpha. By this I can write sin phi. So, sin phi is equivalent to 1 minus alpha divided by 1 plus alpha. Phi is equivalent to tan inverse 1 minus alpha by 2 root alpha, and sin phi is equivalent to 1 minus alpha by 1 plus alpha. If you want to consider alpha value, so then you can write 1 minus sin phi by 1 plus sin phi. So, like this way you can get different values. Why I am giving all these equations means in future gate problems you are going to use any one of these equations to calculate any other value. So, now phi is equivalent to tan inverse 1 minus alpha by 2 root alpha, this is very important one, and here up to now you calculated alpha. So, now here if you want to calculate magnitude, then how you will calculate magnitude? So, this is phi, phase angle, this is okay. After calculating phase for Bode plot, what we need to calculate? We need to calculate magnitude. Magnitude means GC of j omega, modulus of GC of j omega. So, you can see, so this is GC of j omega, this term is GC of j omega term. So, if you consider modulus for this, so here modulus for numerator is root of a square plus b square. So, 1 plus omega square z square divided by, so here I am having in denominator root of 1 plus omega square alpha square z square. Like this you are going to get, this is modulus of GC of j omega. Here also if you substituted omega is equivalent to omega m, then what will happen? If you substitute omega is equivalent to omega m, then so here what I am going to get, 1 plus, in place of omega square I can write, so already we calculated omega m value as 1 by z root alpha. So here 1 plus z square by alpha, z root alpha means 1 by z square alpha into z square divided by root of 1 plus, so 1 by z square alpha into alpha square z square. You can see this z square will get cancelled, and this z square and 1 alpha will get cancelled. So this is equivalent to 1 plus 1 by alpha divided by root of 1 plus alpha. You can see, so now totally this one is alpha plus 1 by, or if you take in common of this root alpha also you can do, or you can see like this, alpha plus 1 by root alpha plus 1 by alpha, this I am just cross multiplying, divided by root of 1 plus alpha. So this 1 plus alpha will get cancelled, root alpha will be your magnitude. So you can see the magnitude. So root 1 by root alpha will be your magnitude. Like this way, for lead compensator we can calculate phase and magnitude. So you will get like this, your Bode plot for this you will get like this. So this is Bode plot structure of lead compensator. It will come like high pass filter response. You just get like high pass filter response. So now here if you want to solve this network, you need to solve like this. So here these two are in parallel. So R1 into 1 by SC by R1 plus 1 by SC. So these two are in series then after. So here R2 by R2 plus this one you need to consider. So finally you need to compare with this equation. So whatever equation you are having here, with this equation you need to compare that network. So I will show you that. So here what I done for lead compensator is general lead compensator transfer function I need to consider. I need to replace z by 1 by z, and after that I need to convert into j omega form. After that I need to consider phase at omega m. How we can calculate omega m? Root of omega c1 into omega c2. This is omega c1, this is omega c2. Root of omega c1 into omega c2 is omega m. So if you want maximum lead condition, d phi by d omega is equivalent to 0. When omega equivalent to omega m will gives you maximum lead condition. That's okay, that's just condition, I am not taking that. So here if you want to calculate phase and magnitude for Bode plot drawing, then you can take phase like this, general phase. After getting you done so many phases with this equation types. So you need to consider phase at omega m and you need to consider magnitude at omega m. So you will get maximum phase here, your maximum phase will be like this. Your maximum phase is tan inverse 1 minus alpha by 2 root alpha, and maximum magnitude will be 1 by root alpha. So when you are getting that, when 1 by z root alpha is there, then you are getting maximum magnitude and phase. So maximum lead conditions. And coming to the shape of this magnitude and phase plot of this Bode plot of lead compensator, that will be like this. So and coming to this is phase 1 and this is magnitude 1, and here coming to magnitude plot, it will be like high pass filter response, because this is a simple high pass filter network type. And here if you want to solve this network, so see here I am going to solve that network. So these two are in parallel. Total V0 by Vi I am writing, V0 by Vi, total gain V0 by Vi is the transfer function. So this is our assumption. this is standard transfer function, this is network. I am comparing this S domain with our electrical network transfer function V naught by Vi. V naught by Vi is equivalent to R2 by R2 plus R1 1 by SC into R1 plus 1 by SC. So, this is your transfer function. I am just simplifying this transfer function, R2 divided by, so here I am writing like this, R2 plus, so R1 divided by R1 SC plus 1. You can see I am just cross multiplying this and I am cancelling this, and here R2 by R2 R1 SC plus R2 plus R1, and here you are having that denominator, that is R1 SC plus 1. I just cross multiplied R2 R1 SC plus R2 plus this R1, and total this one goes to numerator, and this is equivalent to R2 R1 SC plus R2 divided by, so here in denominator you are having something like this, R1 plus R2 and R2 R1 SC. So here I am taking this as common, so you can see I am taking R1 plus R2 as common. So if you consider common of this R1 plus R2, here if you consider R2 as common, what you will get? So if I take in R2 as common, I will get like this, R2 into R1 SC plus 1. So now similarly, if I consider R1 plus R2 as common, then R2 by R1 plus R2. So here in numerator R1 SC plus 1 by, so here you are getting, so 1 plus R1 R2 by R1 plus R2 into SC. So like this you are going to get. This is what you are going to get. So here where alpha is equivalent to, you can compare with this equation. You can compare with this equation. So you can see this equation will be compared with this equation. So alpha is equivalent to R2 by R1 plus R2. So here you are having SZ alpha plus 1. So in that alpha is R2 by R1 plus R2, remaining Z is equivalent to R2C. So by comparing these two, you are going to get, for lead compensator, you are going to get alpha value as alpha is equivalent to R2 by R1 plus R2. This should be less than 1. It's better to get less than 1, R2 by R1 plus R2, and by comparing Z is equivalent to remaining thing, Z will be here. So we consider alpha is like this. So by taking out this alpha value, remaining is R1C. So your Z value is equivalent to R1C. And if you know alpha and Z, you can get the P value. By substituting all this, you will get your actual transfer function of your lead compensator. So here I considered one transfer function. So I converted into j omega domain and calculated phase, calculated magnitude, previously calculated magnitude, and I considered maximum phase condition to have phase and magnitude values, and I considered Bode plot. After that I came to this network, and in this network, so I calculated that network and I compared with this considered equation. So I got my values, what I have considered, what I need to consider. So in this considered equation, according to this network, I need to consider alpha as R2 by R1 plus R2 and Z is equivalent to R1C. If you know alpha and Z, so we can easily write equation for P as Z by alpha. So, like this way we can analyze lead compensator. In the next class we will see lag compensator.